So I was asked to come up with this title well in advance, and I was trying to think of something which really tied together a bunch of the somewhat disparate things that that we were looking at, and this idea of generalizing Lagrangians in various ways, and I'll list some of the things I mean by that, was really coming up in all sorts of areas, and I thought that might be a nice way to tie a few things together. So recently we've, Alborz in particular, has been going in a somewhat different direction, and while I probably could have changed the talk to talk about some more recent stuff, I thought I'd have some fun with this and make it perhaps a bit much more tutorial than I normally would with these. I'm still not sure how true I'll be to that title. We'll probably deal with some of the controls issues next time. So we'll review Lagrangians and duality. And if you've seen perhaps Boyd's lectures on ADMM, I'll certainly talk about ADMM, but I'm going to try to come at it from a much different perspective. So there'll still be some new things if you are familiar with that. So we'll look at a few ways that you can get the Lagrangian and get main duality results with an eye towards how special is the Lagrangian, and can we have something else there, and when might we want to do that? So we'll look at that two different ways in particular, and then we will look at ADMM, which is one particular type of generalized Lagrangian, which has been a really hot topic the last few years, particularly in some signal processing applications. And we'll look in particular at what happens when you apply this to the lasso, which is a nice example to kind of feel out some of the freedom that you can get from some of these ideas. And then there's also something within that ties into to a problem I've been interested in for a couple years, which is whether there's some way to solve the lasso in a recursive manner. All right, so just like I do in my class, I'll try to give both examples where everything is just a real number, so we can get some intuition, and then also generalize things, so that those of you who do like that can see that as well. And there's often some really beautiful ways things actually simplify when you generalize. But we'll have this as well, so that if you're not as comfortable in general spaces, then you can just think of this example instead. All right, so our canonical mathematical optimization problem, we're trying to minimize some functional of some primal variable x. We have a bunch of inequality constraints. So for now, we're just assuming that each fi just gives us some real number, and we want those all to be less than or equal to 0. And we have some equality constraints. So these hj's all have to be equal to 0. And we say that the problem is convex. So in this case, where all the constraints are just less than or equal to a real number or equal to a real number, the problem is convex if all of these inequality constraint functions are convex functions and all the hj's are affine. Right, so this so far should look very familiar to people in my class, and most of the rest of you as well. So let's see what we can do with that and actually derive the Lagrangians. So one of the things I dislike about several books that just kind of give you the Lagrangian, and then you work out what you can get from there. Whereas you can, in one slide, really, one or two slides, we can just play with the original problem and kind of rewrite it and just have the Lagrangian fall out. And then not only is that nice in and of itself, but you get a nice understanding of what might you be able to replace it with. Okay, so we say that the value of this problem, when you solve this, is p star, or the value of the problem p, which is the infimum over all of our over our domain of this objective, subject to the constraints being satisfied. So we could rewrite that as minimizing over the objective, and then plus, and just looking at cases for each constraint, if the constraint is satisfied, so if these are non-positive or if these are 0, if the constraint's satisfied, you just add a 0, because that's good, it's satisfied, everything's fine. And if it's not, you add infinity. Because if any one of them is violated, then you don't care what the objective is, the point's no good. Okay, so now getting rid of the cases, we're minimizing over the whole domain of f naught of x plus 0 or infinity, depending on whether the constraints are satisfied or not. So now we can rewrite that, and let's look at the equality constraints first, where it's even more clear. Okay, we want 0 if this thing is equal to 0, and infinity otherwise. Well, if we introduce this new variable nu j, and take the supremum over that, well, now if hj of x is not 0, you can blow that up by letting nu j go to plus or minus infinity. And if it is 0, then this will be 0 no matter what. So these cases are equivalent to just writing this supremum. And then similarly for the inequality constraints, here you have to choose over non-negative numbers lambda. If fi satisfies this and is negative, the biggest you can make this is 0. And if it's positive, you can blow it up. So once we've rewritten it like that, we can pull out the supremums, and we get that our original problem is equal to the inf over the primals, the sup over these will be the dual variables, these lambdas and these nus, and this is what we're left with in the middle when we take the objective and the things we were supremizing over. So that we can call the Lagrangian. Okay, so just starting with that, P star is the inf sup of the Lagrangian. And now we know if you've looked even a little bit at game theory, the inf sup is always bigger than or equal to the sup inf. All right, you'd rather play second. So min max is bigger than max min, and vice versa. So once we've written it in this way, we have this min max way to introduce duality. And we can just say the inf sup is bigger than or equal to the sup inf. And then this thing we'll call our dual function. So now we want to supremize over that, and that gives us the value of the dual, or d star. All right, notice we haven't said anything at all about convexity yet. Everything we've said just holds without any extra assumptions. And this is the only inequality we had, is when we flipped around the minimization and the maximization. So then we also get strong duality, meaning we already had equality everywhere but here. So we can say this is equal if Lagrangian is convex in the primal, which follows as long as the problem was convex, which we said meant the FIs are convex, the H's are convex. So that'll make this convex in X. And if L is concave in the dual variables, when in fact it's affine in the dual variables, so that's satisfied. So of course there's books written on when min max is max min, and we're not going to get into the technical conditions. The most common one for our purposes here is Slater's. But the idea is we want to isolate the key properties. And the key properties are, if X was feasible, we want it to be able to blow up. If X is feasible, we want the sup to just recover the objective. If X is infeasible, we want to be able to blow up the Lagrangian. And in fact, even that's stronger than we need. We just need this to be bigger than P star, really. But usually that will go to infinity. And those two things alone already give us weak duality. That already tells us that P star can be written as the inf sup. So then when you flip that around, you get the dual. So 1 and 2 are all we need to already have weak duality. And then assuming that we can satisfy some usually very mild technical conditions, we need convexity in the primal and concavity in the dual to be able to make that strong. All right, so in other words, that Lagrangian that I'm sure we're all very familiar with, that's not the only option there. All right, we didn't have to. We could have looked at the maximum of these violations. There's lots of different things you could do to get these four main things that we needed. So here's one way you could tweak this, which will come up in ADMM, which is to take the Lagrangian that we had and add on the squared 2 norm of one of the equality constraints. All right, so if we think about that, if x is feasible, well, we know L recovers the objective, and now if x is feasible, this just goes to 0 anyway. And if x is infeasible, then we can still blow L up. So that's fine. We certainly don't lose concavity in lambda or in lambda nu. And this new term is a 2 norm squared, so it's still convex. All right, so there's various, I was using the term pretty broadly in the title of generalizing the Lagrangian. So there's 4 things, and we'll mostly focus on the first and the last one here. The first one, which isn't really a generalized Lagrangian, that just brings us back to what mathematicians would refer to as the Lagrangian, is to just generalize these constraints, no longer require that we just have things less than or equal to 0 or equal to 0. So we'll quickly go through what that looks like. You can also consider a richer class of dependence on these dual variables, so that while you so that you'd have a better chance of getting better weak duality. Or if you're supremizing over a larger, so not just affine functions of lambda and nu. So we're not going to talk about that anymore. The third one here, not going to talk about after the slide either, but it's there'll be a lot of we're typically going to let our dual variable lie in this dual space, as we'll see. And basically, one thing I've been interested in over the past few months that sounds really technical, but I'm getting more and more convinced that it's actually could be kind of crucial in controls, is to see where you can replace the dual with the dual space with the pre-dual space. And the reason that might be important is in control, where we often end up in H infinity, we don't know what the dual space is, but we do know what the pre-dual space is. So again, don't worry, I'm not going to dive into that anymore today. I just want to list that as one of the many things that we might want to generalize, and it's something I think could be a lot more important than it sounds for something that technical. And last ones we've already hinted at. The example is to just look at different functions that still serve the purpose of the Lagrangian, such as these augmentations. So other functions that are convex in the primal, concave in the dual, and satisfy the other conditions, such as augmentations. Okay, so we'll go much more quickly, since it is very similar, through what happens for when we generalize the constraints. So we can very broadly just say we're minimizing some functional over some domain subject to some constraint function g having to lie in a set n. which in the end will have to be a closed convex cone to be able to get strong duality results out of this. But we call this the negative cone. All right, and the way we'll typically want to rewrite this, if you just let k be the positive cone, just be negative n, you can write this as a generalized inequality. So this just means that g of x is in negative k. So this means the same thing. But now it looks more like the problem that we're used to. And we say that this general problem is convex if, again, the objective function is convex, and now if this constraint function g is k convex. And one of the things I think is really nice, both just about the setup and also when you look at the duality results, is this this really broad, simple setup not only allows you to generalize the inequalities, but it also allows you to unify inequalities and equalities. Because this could just mean that certain parts of g have to equal 0. Right, 0 is just the set that only has 0 is a closed convex cone. So equality constraints are built into this, or can be built into this as well. So we can just look at all this like we just have one big constraint. And everything follows very similarly. We're minimizing f of x subject to that constraint. We want, can rewrite that as we're adding something that's 0 if it's satisfied, as infinite if it's not. And then we can write that as the supremum of the constraint with our dual variable lambda. And the only part you'd really have to think about more if you want to go away and verify this is that this works if lambda is in k star. All right, so just to think of that as far as recovering what we had before, if g is telling us that something has to be non-negative, then this would recover that lambda has to be a non-negative number. And if we had an equality constraint, well, the dual cone of 0 is everything, is the whole dual space. Just like before, our news could be any real number. So yeah, I think it's kind of nice how when you look at this that way, that equality, inequalities, they all fall out from this. And when you take the equality constraint and say that you want it to be k convex, you actually recover that it has to be affine, which we usually just assume. So that all falls out nicely. Our general Lagrangian is then f of x plus the pairing of the constraint function and lambda. And then the rest is basically the same, infimizing over sorry, the new should be gone now. Over that gives us our dual function, and we want to maximize over that. And now we get equality, again, if L is convex in X, which does follow from the convexity of F and the K convexity of G, and concave in lambda, which again we have affine in lambda, and some technical conditions, which are usually pretty trivial. And so we again have 4 key properties. We have feasibility, we recover the objective. Infeasibility, it blows up. And we want convex in the primal and concave in the dual. 1 and 2 give us weak duality. 3 and 4 with technical give us strong duality. Okay, so that's one way you can derive the Lagrangian and get your key duality results with this min-max or saddle point approach. There's another way, and when you do that, or if you're just handed the Lagrangian, you can often look at results on sensitivity as something that that can be derived from that. But there's another approach that I've tried to introduce to the class for the first time this year, where you instead view duality as being all about sensitivity, all about can you tweak the problem, get some new large class of problems, All right, so embed the primal problem in a larger set of problems, and then use that to get these duality results. So typically, this larger set of problems will be found by freeing up the values associated with the constraints. So instead of saying this has to equal 0, we'll say it equals some variable. And now for that each variable, you could solve the problem and get a different solution. And then once you do that, once you get this whole family of solutions, you can look at the conjugate of the conjugate, which will always give you a lower bound. So right there you get weak duality automatically. And then under certain conditions, which then can be pulled out from everything we know about conjugate functions. And you can more automatically. So I mean, before when we were talking about tweaking the Lagrangian, you'd have to kind of each time rework, make sure those technical conditions are right if you tweaked the Lagrangian and wanted to get various things out of it. With this approach, it all falls out from everything we know about when does the conjugate of the conjugate recover the original value, and so that kind of thing can be a lot more automatic. All right, so under conditions, and we'll just briefly mention one of them, the biconjugate at this unperturbed value will recover the original value, and you'll get strong duality. Okay, so let's see what this looks like. And it'll be helpful to just think of an extended functional that gives us the objective if we have a feasible point and blows up otherwise. All right, so in other words, the original problem is just to minimize f tilde, right? Because it blows up when you have an infeasible point. And so a perturbation function, all it really needs to satisfy to be a perturbation function is it can be anything that if you plug in 0 for its other value, so it'll take the primal and it'll take something else. And as long as you put in 0 for that something else, you need to recover this original thing that you're trying to minimize over. All right, so just to give the most typical example, so we can kind of get our head around what this might look like, but keeping in mind that it can be much, much more broad. Most typically, we'll make this perturbation function give the objective if the constraint function is less than or equal to some z, and infinity otherwise. All right, so then if you plug in z equals 0, you get back to the original function. If you plug in z equals 0 and try to minimize this, you get the original problem. All right, so now the primal problem is recovered by, like we said, plugging in 0 and minimizing. Plug in 0, you get the original f, minimize over that. And we get our whole family of perturbed problems by instead minimizing over our perturbed phi. All right, and we'll call that, so I know Boyd calls it P star, and Lowenberger calls it omega. I like to stick with omega since the whole point of this is that we're going to be taking the conjugate, so I don't want to call it something star, and then we'll just have stars meaning all sorts of different things. So omega is sometimes called the sensitivity function or the primal function. That tells us the value when we minimize over this perturbed problem. Often meaning we relax or tighten the constraints, but it can be much more broad than that, as we saw. All it means is when you put z0, you get the original one. And typically we'll also want to make it so that if we originally had a convex problem, phi is convex. All right, so then by definition, P star will be omega when you put in 0. And we can compare that. So now we have this whole family omega that varies with our perturbation. Put in 0, we get the original value. And now we can compare that to omega star star of 0, which will always be less than omega of 0. All right, so now we can write our main summarize all these results as P star is the minimum over the unperturbed phi, which is by definition omega of 0. From what we know about conjugates, that is bigger than or equal to omega biconjugate of 0. And then when you work that out, just from the definition of omega, work out what is the biconjugate and plug in 0, what you get is that it's the supremum over all lambdas in the dual space of this thing, of the conjugate of phi, but with a 0 in the first argument. So you get this nice thing where your primal is then phi with a 0 over here, and your dual is phi with a 0 over there. And unfortunately, I think these things arose in different areas before it was realized that they were intimately related, so you get signs that aren't quite what you want them to be. But aside from that, it's this really nice way to look at it, where you have 0 in one, 0 in the other, and then that's d star. So in this, you can look at this as g of lambda from before. That's the dual function that we're trying to supremize. That will at least give us a lower bound and might give us equality. And the simplest condition to guarantee that those are equal from this perspective is if omega is convex. And omega is, you can show pretty in a couple lines, omega is convex if the original problem is convex. If omega is convex and it's continuous at 0, then these will be equal. All right, so as long as nothing funny, it's convex and nothing funny happens if you make a slight perturbation, this will be a way to get strong duality. All right, so now if we do use that, let's look at three examples to feel this out a little bit. Using the most typical example where we'll just say that phi is f, and then perturb the constraint. And then if you work out what this is, or what g of lambda is, you get that it's the minimum over what we previously defined as the Lagrangian, as long as lambda is indeed in the dual cone of k, and minus infinity otherwise. So you, just by looking at this as this perturbed problem, and then cranking through this conjugate machinery, the Lagrangian falls out again. And we find that the dual problem is to minimize over Lagrangian and then supremize over lambda in this dual cone. All right, well, let's see what else, some other ways we could write phi and what else we'd get out of it. Let's first see if we can pull out that same perturbation that we had before, which it said would be related to ADMM. So we can instead write phi. So this is exactly what I had before, where it blows up if the perturbed constraint is infeasible. And if not, instead of just taking the objective, we'll take the objective and add on this term, the norm of h1 of x. You just assume h1 of x is a equality constraint that's part of that our one big constraint. Yeah.
The meaning of h1 is compared to h again?
Yeah, so I'm saying g, so here I've used the framework where we just have g containing all of our constraints. Right, so part of that could be that,
okay.
Yeah, so say, if g takes you to R5, you just say the fifth part of that has to just be equal to 0, so you have an affine constraint as part of that we can just call h1. So it's sort of mixing the frameworks a bit, but I think it's okay. So all we need, remember, for this to be a perturbation function, we want it to be convex. It's what we had before, but with this thing added on, so it's certainly still going to be convex. And we just need to know if we stick in 0, we recover f tilde. Well, indeed, if we put in 0, that means that this is going to, at z equals 0, that term is going away anyways. So it's perfectly fine to add it here. And then when you go through, find the conjugate of this, stick in 0 to find the dual function, we get that perturbed, that augmented Lagrangian from before. So that's the only example like that that I'll do here, but I think it shows how much freedom you really have to perturb this in any way, as long as you get the same thing at 0, and then you can work this through. One other example I'll do, because I think the other type of duality that's best known is perhaps Eventual Duality, and it's nice to see that you can pull that out of this framework as well. So if we want to minimize just some f of x plus some g of x, all right? So I mean, usually we think of duality, you've got to have constraints, right? Or else there's just nothing there. Well, this shows that the whole thing can be much more broad than that. So I want to minimize some f of x plus some g of x. Then we can write a perturbation function. It's just f of x plus g of x minus z. Obviously, plug in z equals 0, and you get back the original problem. So then when you work this out, you get that g of lambda is minus the conjugate of f of lambda minus the conjugate of g of minus lambda. And so the most common interpretation of this is if f and g are convex, you can look at this as trying to find the difference between a convex function and a concave function. So you're trying to find the x where the difference is smallest between some convex and concave function. And this Eventual Duality tells you can find tangent hyperplanes or tangent lines if you're just in one dimension. And the problem is equivalent to how far can those tangent planes be spread out. And so I'd always kind of learn those things pretty separately, and I thought it was nice to see that they can both just fall right out of this whole perturbation framework.
So this relates to Pareto also, right?
To what?
To Pareto frontier.
I've been assuming that
Because if you try to put different weights in front of f and g, just do trade-offs.
yeah. So you're assuming you scalarize the
Put some coefficients that sound to 1 and then vary them in the same problem. Then you can actually trade.
yeah. You'd actually asked a similar question when I taught.
The question is, can you use actually that to compute Pareto function by any efficient algorithm rather than doing it in a stupid way by taking out the function making the constraints and the minimum? Which is an active area.
Okay.
To compute directly Pareto functions.
Okay. Yeah, I'd actually suggested something similar to someone behind you for a project.
I mean, there's something that I know is called maximum diversity method, but there are many others. There's a whole theory about what do you do on the Pareto frontier going from one point to the other that plays around with these ideas.
Okay. But yeah, one of the things I hadn't generalized, I'm assuming f is a functional, so yeah, it doesn't quite address that. But is that actually what you're doing for your project? Or? No? Oh well. Okay, so the main ideas in ADMN, which sometimes get thrown together, are variable splitting, which by itself can be very useful. It's actually what we're going over in class tomorrow, and we'll briefly go over what that is here. It gets combined with this augmented Lagrangian, and then there's also an element on the algorithmic side. Once you've set up your problem in a certain way with this variable splitting, you've set up your Lagrangian in this non-standard way with this augmentation, and there's this third component of how you do the optimization, and you need all three components to get the main benefits out of it. So we'll see what those are. So the main reasons that you want to do this, one thing is strong convection. So I haven't shown exactly what it is yet, but when we looked at the augmented Lagrangian, we saw we were adding, that I said was related to this, we saw we were adding this 2 norm squared. So we're adding this strongly convex term, which means that we'll always be able to have a unique minimizer of the Lagrangian. Now that can be really important, because if you want to, if your dual is easier to solve than your primal for whatever reason, or you want to solve them together as we often do, if you solve the dual, you'd like to be able to plug that into the Lagrangian and minimize it to find x star. But you can only do that if you can only be guaranteed to be able to do that if you have a unique minimizer. And that unlike some other technical conditions we've talked about, that one's not one that just is trivially satisfied. In fact, an LP is not satisfied for an LP, to take just the most common example. So this can be really useful for problems where you wouldn't have had strong convexity in the Lagrangian to give you that. So then you have a unique minimizer, and you can say things about the convergence of x as your lambda is converging as well. So the computational considerations, I won't, that's related to that. Having the strong convexity can help it. I'm not going to focus on that today. Decomposition, as we'll see, so if you have a problem where you want to be able to break it into several small problems, or at least break some part of your problem apart so that you can solve it in a bunch of chunks, either because it's enormous and you can't solve it together, or because you physically aren't going to be able to have all of your information in a centralized place. That's another reason. And the other one, which is one of the things that kind of caught my attention in it when I was starting to read up on it, is it can also help with recursion. So like I said, I've been interested in seeing if you could update the lasso with new data points. And as we'll see, that when you apply ADMM to the lasso, some nice things fall out in that regard. But more generally on the last two, it just allows you to address different parts of the problem at a different time, so that you might be able to do things like this. All right, so this can certainly be made more general, but we've already shown we can generalize things quite a bit. Now let's make sure that we can get the main points of ADMM across clearly. So consider where we just want to minimize some f of x and some g of cx. And you can certainly have other constraints on here, but just to be clear, they're only removed to make the next few slides more clean. But you could certainly have other constraints on x that are on here. All right, so the first part, which is the variable splitting part, and this by itself is something, either if you have, physically f can be minimized in one place and g in another, or sorry. So we'll just say we're just going to call this z. Right. So for now, avoid the fact that these are tied together. Say this is f of x, this is g of z, and then tie them together in a constraint where we say that cx is equal to z. All right. So if we just looked at the Lagrangian for that, you get f of x and g of z, and this new transpose cx minus z term. Then we also augment it in the way that we showed as examples of Lagrangian that satisfied our conditions, or of our perturbation example, by adding on this 2 norm squared of cx minus z, of the residual, if you'd like. All right, so this is the thing we want to be equal to 0. And now we're penalizing it in addition to having the duality term. All right, and you could, certainly if you hadn't learned anything about optimization and you tried to do something like this, the first thing you might try would be to just penalize the residual. Then you'd, of course, have to let rho go up to infinity to approach the solution. And here you won't have to do that because you have the dual term as well. So it brings those ideas together of the dual term and the penalty term. All right, so you could gather, if not for this augmentation term, you could gather the x's together here and gather the z's here. And then when you went to find the dual function, you can call it g rho. We're infimizing over the primal, which is now x and z. And that would be, you would be able to separate those into a minimization over this and over that. So the variable splitting allows your minimization of the Lagrangian to nicely break apart. So now we've kind of ruined that by adding this term. So that's where the algorithmic side of ADMM comes in, which tells us that you can minimize over them separately. All right, so you find x by minimizing Lagrangian over x while fixing your z and your dual variable. And you can find z by minimizing just over z while fixing the others. And then there's an update for nu that's just based on the residual. So this one has this nice economic interpretation that we often get with the dual, where if this is too high, you raise the price of it, and then it'll come down in the next iteration. If it's too low, you lower the price, and it'll get larger in the next iteration. And it works with this fixed by using the rho parameter in front of the residual to update anew. All right, so this deals with this trade-off where we want to be able to have our variable splitting, but we want to have the nice computational properties that we get from having this strongly convex term. And this, in some senses, gives us the best of both, because we'll still be able to split, minimize over them separately, and we'll see that often leads to a mostly split solution, and we still have the strongly convex term in there. All right, so under pretty mild conditions, you get convergence of the second primal of z, of the dual, and convergence to p star. And under some more conditions, you can get convergence of x as well. All right, so you can rewrite this. Say for the first one, you're minimizing over x. So by ignoring the terms in z, by ignoring the z terms and then bringing together the dual term and the augmented term, you can rewrite the minimization as f of x plus, and bringing all those terms into one norm squared term. And the same thing happens for z, minimizing over g of z and the norm of one norm term. So a nice way to think about this that we'll see in particular for our lasso example is now we want to minimize f of x, but keep x or keep cx close to z. And we want to minimize z while keeping it close to x. All right, so if it was hard to minimize f of x and g of cx together, but you can minimize it while just keeping x close to a certain value, which is exactly what happens for the example we'll see, then this can be really helpful. And yeah. All right, so I'll take this one step back to tell you about this problem that I'd been interested in. Then we'll apply ADMM to the lasso, and then we'll see how, in addition to the things that you could read about in lots of places about the nice things that happen there, you'll also see what kind of opened my eyes there to how this could be helpful for this problem as well. All right, so I think we all know by now, if you take a problem where you're minimizing the sum of squared errors, or the 2 norm of y minus ax, and you penalize your coefficient with the 1 norm, that tends to encourage sparsity on x. All right, so this is called the lasso. The original lasso paper actually had a constraint on the 1 norm, which is why I've specified this is the penalized version of it. So it's been known for a while that encourages sparsity, and recently it's much better understood why and when you can have some guarantees about the results from this. But encourages sparsity in x is all we need to know at this point. So what I wanted to understand is there some way, like you would with, like you could certainly do if you had a 2 norm penalty here, or even if you had dynamics and were doing the Kalman filter, you can get your estimate, you can get a new data point, and you can update your estimate without having to go and save all your data and resolve the entire problem. So I was interested to know if you could do something like that for the lasso. Could you solve it, get a new data point y along with a new row of a, And could you just update X without having to go back to all of your other data? Either if you have an enormous problem, or if, like we often have in engineering, you need to have a running estimate as you get more and more data. So the first thing I tried in 08 was to take the Bayesian view of this problem. So just like if this was a 2-norm penalty and you're doing ridge regression, there's a Bayesian view that you had a prior distribution on your coefficients that was Gaussian. There's a Bayesian interpretation of this, that you had a prior distribution that was double exponential or Laplacian. The problem there is, with a Gaussian, you keep your mean, keep your covariance, get a data point, update it, and that's how it works. With the Laplacian, you get a data point, and the posterior distribution doesn't look like anything that I know of that can easily be. There's nothing you can still classify with 2 things. So the first thing I tried was to approximate that with something you could update, and it worked very well. But of course, it worked well. It was exponential in the number of parameters, and while that wasn't necessarily catastrophic, since it's telling you as it goes which variables you don't have to worry about, while we were trying to think of the best ways to leverage that for some larger problems, there's some other people came up with some really nice solutions that I like a whole lot better. So I'll just summarize 3 of them. So there's people in Minnesota address this same problem by just showing that here you get, you're trying to minimize this quadratic function of x, and each term, the quadratic term, the linear term, the constant term I guess doesn't, and the constant term, they can all be updated recursively. So it doesn't directly update your x star, but if you've just made some small changes to your parameters, you take your old solution as your new solution, and you should have a very small distance to move. So you just kind of do this warm start and keep updating the convex problem that you're trying to solve. The homotopy solution was really nice. It's also nice in that if you've heard of Lars, where Lars least angle regression solver. The problem there is, and I had something similar in last year's final, is if you have a solution to this and then you change your mu, how can you, so if you make a small perturbation to mu, how does x star change? All right, and you can look at the KKT conditions and see that it'll move, x star will move linearly until you hit a critical point where something becomes 0 or leaves 0. Then they move in a new way linearly until a new critical point. And so this approach took that same approach of looking at the KKT conditions and seeing how everything would slide. But now the thing that slides is you look at this with a new data point as the old thing you're trying to minimize, but adding on yn plus 1 minus the new row of A transpose x. So the new error term times some epsilon, put in epsilon 0. At epsilon 0 you have your old solution, and now you just need to let epsilon slide towards 1. And you can look at the KKT conditions and see how they would slide, and you get, it's a little more complicated, but it's the same kind of idea as Lars, where you can then see how the solution will slide. So, I'd be interested to see how these all compare, which I think we still don't really know. They've all kind of just been written by different people, and it's not really clear which would be, for instance, if the homotopy doesn't finish, and then you get your next data point. So I'd kind of like to understand which is the best solution under when you can't execute any of these perfectly. And the last one, Bhavati, who's coming here within a month or so, he address this problem as well by looking at an expectation maximization algorithm and showing that you can just update one part of it. Okay, so now let's see what happens if we use ADMM on the lasso problem. So this is what we want to minimize. We can do this variable splitting and say, okay, we got the sum of squared errors here and the one norm here. Well, let's just call this z, and then set x equal to z. So now we'll be separately trying to deal with the sum of squared errors, trying to keep the errors small on one side, and then trying to keep the one norm small separately. Okay, so looking back at what we worked out before for our iteration to optimize over x while keeping everything else fixed, you get that you want to minimize the sum of squared errors, and this other term, which is a 2 norm squared of, and these are just constants at this stage. All right, so we have x minus some constant, 2 norm squared. So that, in the end, is very similar to what you do in a ridge regression, where you try to keep the sum of squared errors small while penalizing the 2 norm of x. Here's the same thing, except it's x minus some constant. And that's solved by something that indeed looks very similar to ridge regression or penalized least squares or Tikhonov regularization, where you have a transpose A plus, sorry, there should be a row I identity here, inverse times A transpose Y plus this constant. Now for the Z update, plug in the one norm for G of Z here, the mu times the one norm. And now what you're trying to do is trying to keep the one norm of Z small while trying to keep Z close in 2 norm to this constant over here. So if you think about that, near 0, the one norm is bigger than a quadratic. All right, so if this constant is small enough, then the one norm is going to be dominating the quadratic, and the best solution will be to just have Z actually be 0. So the solution to this is this soft thresholding, meaning that if this constant, so this is the constant term from here, if that's within mu over p, then this just goes to 0. And if it's bigger than that, then you reduce it in absolute value by that same amount, mu over rho. All right, so it gets pulled towards 0, and if it's already close enough, you just make it 0. So I think this is what's really, oh shoot. Oh.
You're almost finished.
All right. What's nice about this thing that you don't get with some of those others is you get a real 0. It's not 10 to the minus 6, and we cause it. I mean, this is just saying at this point in the iteration, it will set certain values to 0. And I think it's also a nice way to see, amongst the many ways we try to understand why does the lasso work, why do you get sparse solutions. There's lots of ways. We can look at it. You can draw the one norm ball and see that if you try to make it close to a certain point, you're likely to end up at a corner and all that. But I think this is a really nice way to see it too. You say once you know you need to be near some constant and minimizing the one norm, you'll actually get zeros if that constant is small enough. All right, and then we have our dual update based on the residual between x and z. So just gathering all of those updates, where we have our ridge regression-like update of x, our soft thresholding for z, and our update of nu. So what you notice here is that, so the nu is completely distributed. All right, this can be, so if nu has 1,000 dimensions, each one of them can be done separately here, right? In each dimension, you're just looking at this difference and using that to update nu. Same for z. All right, you've got this constant let's say it's in 1,000 dimensions. For each one, you soft threshold it. So those can all be done in a completely distributed fashion. And the only part that's not distributed is the update of x. All right, so that's one thing that you often see about this. The thing that, because I've been looking at this recursive lasso problem, the thing that caught my eye when I first started looking at this is, wait a minute, where does, say you get a new measurement, a new y, a new row of a. Well, this doesn't change at all. And this is a similar flavor to what Babadi had found with the EM algorithm. This doesn't change at all. This doesn't change at all. The only place the new data comes in is up here. So I've been working on that with Tingyu a bit over the summer, trying to find good ways to go through this, and then you get a new data point, so then you have to adjust, have to update your A transpose A. And so while Babadi's is much more, exploits the problem, and and the key is avoids having to update an inverse, so it's generally a lot faster. But I still thought it was interesting to try to work this out, because it is derived in such a general fashion, and perhaps will be more useful when we try to bring, say, dynamics into it, try to solve a problem like the Kalman filter, while putting something like a one norm penalty. So I think it's nice that this really general setup leads to something like this. And in general, it's kind of liberating when you start playing with problems like this. I felt that way, and I know everyone in 6-9, when I ran the seminar last semester, kind of felt the same way when we started looking at these. Because you can just, if you've got this one thing you can solve and this other thing, you can, for the most part, break it apart. And I should wrap it up, but that's one of the reasons I'm very excited for trying things like this in control. Is in control, the problems we can solve are, for the most part, really fragile, right? I mean, you say you can minimize an H2 norm, you can minimize an H infinity norm, try to add them together, and it's an extremely difficult problem. In the area I've looked at the most, the same kind of issues arise, even if you have the type of decentralized control problem where you can write it as a convex problem. There's still no obvious way on how to deal with the resulting convex problems. So so I think this kind of approach, where you can try to break apart different parts of the problem that you can solve, could be a really exciting area in controls, and we'll talk about that more next time. Thank you.
Time for questions, I think.
It was all just review. It was all just review.
Yeah. I don't think it's going to be that easy for controls.
No, it's not.
Because you have everything. So.
I was going to show some things we tried that didn't really work, but then I remembered that the camera's here, and I shouldn't do that just yet.